In laboratory this week, we're going to look at substitution reactions, starting with alkyl halides. And we're going to look at different reaction conditions and see how they affect the rates of these substitution reactions. In nucleophilic substitution reactions, we have something that acts as a nucleophile, right? This is something that is a Lewis base, and it's going to cause another group then to act as the electrophile, or Lewis acid. And what's important is that this other compound has something that can act as a leaving group, right? Something that can take those electrons and break that bond as the nucleophile forms a new bond with that carbon, right? So in order to be a good leaving group, right, something has to be stable with this pair of electrons. So a good leaving group is a weakly basic, stable molecule or ion. Okay, so there has to be something on our electrophile that can act as a good leaving group. And so that's why it is a substitution, right? We remove the leaving group and replace it with a group derived from the nucleophile. There are two general patterns of nucleophilic substitution. In one of the patterns, the nucleophile actually collides with the central carbon at the same time as the leaving group is leaving, right? So there is an actual collision in this one step between the nucleophile and the alkyl halide. So that makes the kinetics, right? If we look at the rate of this reaction, right, it's proportional to both the concentration of the nucleophile and the concentration of the electrophile, often an alkyl halide. Okay? And so that makes this reaction second order. And so we call these reactions SN2 reactions. Substitution, nucleophilic, second order. In the other pattern of nucleophilic substitution, the leaving group leaves first on its own and creates a carbocation. Right? So the leaving group leaves. Again, it has to be a weakly basic, stable molecule or ion. And then that carbocation becomes the actual electrophile that will interact with our nucleophile. And so the nucleophile can donate its electrons to that electron deficient carbon in the carbocation to create a new bond, right? And so the substitution occurs in two steps, right? The leaving group has to leave on its own first, and then the nucleophile can come in to replace it. Now this step is slow, therefore it is rate limiting, right? It determines the overall rate of the process, right? The slowest thing you do determines how fast you can get the whole thing done. And since it involves only one reactant, if we look at the rate equation for this, the rate is just equal to the rate constant times the concentration of the substrate with the leaving group. right? And so that makes this a first order process. And so we call these reactions SN1 reactions. Substitution, nucleophilic, first order. One of our most popular groups of leaving groups in nucleophilic substitution reactions are the halide ions, especially the chloride ion, the bromide ion, or the iodide ion. Today in lab, we're going to be using chloride ions and bromide ions as leaving groups. So, halide ions are good leaving groups, right? Because in their negative forms, right, they are the conjugate bases of the hydrogen halide acids, and so they are very weak bases, right? So they are weakly basic, they are stable, and they're stable under all reaction conditions, right? And so alkyl halides make good substrates, that is, good starting materials for nucleophilic substitution reactions. So in our first reaction pattern, we're going to react our alkyl halide with sodium iodide in acetone. Okay? Now, acetone, right, here's our structure of acetone. It's an aprotic solvent, right? I know that, right? That is a single word, aprotic. Okay? It is an aprotic solvent, meaning there's no hydrogen ions or no hydrogens on the electronegative atom, right? That oxygen doesn't have any hydrogens on it, right? So as a result of being aprotic, it doesn't strongly solvate an anionic nucleophile, right? That is, it doesn't surround the nucleophile, which means the nucleophile can act as a better nucleophile. It also doesn't strongly solvate an anionic leaving group. So therefore, it doesn't stabilize the leaving group more. But it also doesn't block the nucleophile. Right? And so letting the nucleophile work better and not helping the leaving group leave sooner promotes an SN2 reaction over an SN1 reaction. So under these conditions, we will assume that our reactions are going SN2 if they go at all. So here's a layout of the mechanism of our reaction, right? So here's our acetone solvent. We said our acetone solvent won't interact strongly with our leaving group, so it doesn't help the leaving group leave, right? Something has to sort of push the leaving group off. But it also doesn't surround our nucleophile, so that our nucleophile is free to move close to that electrophilic carbon, right? So if we're laying out our mechanism, right, we started our electrons, draw our arrow to the carbon where the new bond will be, right? And then show our leaving group taking the electrons. Okay, so we get an SN2 product. Now there's another feature here. If we look at sodium iodide versus sodium chloride or sodium bromide, that is our reactant sodium halide versus our potential product sodium halides. The iodide ion is much bigger than the chloride ion or the bromide ion. So the ionic attraction between sodium ions and iodide ions is weaker than the interaction between sodium and chloride ions or sodium and bromide ions. And so what happens is that sodium iodide is soluble in acetone, right? Acetone can create interactions to pull sodium ions and iodide ions out of that crystal, while sodium chloride and sodium bromide are insoluble in acetone, right? And so what happens is this sodium halide salt precipitates out of this acetone solution, which if it precipitates a little bit, it makes the solution look cloudy. But if it precipitates a lot and very quickly, you might actually see solid. So what we're looking for as an indicator of this reaction is this appearance of a cloudy solution, or even seeing some solid, as an indicator that you're making the sodium halide that precipitates out of that solution. So you will time the appearance of the cloudy solution or the appearance of solid from the time you mix your reagents. And so what we're looking for is two things, right? Which R groups react faster, right? And also which leaving groups react faster, right? You should consider both comparisons as you're writing your conclusions. In our second reaction, we're going to react our alkyl halide with silver nitrate in ethanol as a solvent. Now, ethanol is a protic solvent. That is, it has a hydrogen on an electronegative element. So it can act as a hydrogen bond donor. Okay? Now, protic solvents strongly solvate anionic leaving groups. That tends to stabilize leaving groups, right? So they stabilize the leaving group. Now, this can also, right? It's got unshared pairs of electrons. So our ethanol in this reaction is also going to act as our nucleophile. But it's neutral and it hydrogen bonds. So it's going to be a weak nucleophile, right? It's uncharged. It's involved in a lot of hydrogen bonds within the solution. And so it will tend to be a weaker nucleophile, right? It also tends to solvate the nucleophile. And so, as we talked about before, that tends to block, right, the effect of the nucleophile. Right? So the sum of all of these effects is that a protic solvent tends to promote SN1 reactions, right? By helping the leaving group leave, by slowing down the nucleophile, right? And in this case, by acting as a weak nucleophile itself, okay? So here's going to be a layout of our reaction mechanism, right? We start with our alkyl halide, right? Our leaving group leaves on its own, right? Creating a carbocation, right? A carbocation intermediate, right? And our leaving group halide ion, right? But this is in a silver nitrate solution. And if you remember back to our general chemistry solubility rules, most ionic compounds involving silver are insoluble, right? Silver nitrate is one of the few that is soluble. So when we create the halide ion in the presence of the silver ion in that alcohol solution, that precipitates as silver iodide, right? So that is going to be, right, that appearance of precipitate is going to be an indicator that we have a reaction. Now, that doesn't complete the reaction, right? We've still got our carbocation hanging out there, right? So our ethanol will act as nucleophile, attack that carbocation, right? Which creates that new bond, but leaves the ethanol positively charged, right? We end up with a protonated ether, what we could call a dialkyl oxonium ion, right? And so another molecule of our ethanol can act as a base, take that hydrogen ion, and then we end up with our ether product, right, that we can't see. As we said, the appearance of the silver iodide precipitate is our indicator of reaction. So again, right, this is a reaction that is causing a precipitate. So again, we're going to measure the time to get our precipitate. And we're going to look at both the structure of the alkyl group and which leaving group is on there, and evaluate the effectiveness of both, the reaction rate with considering both the structure of the alkyl group and the identity of the leaving group. Right? So in reaction 3, we're going to use the tertiary butyl bromide as the substrate for all of the reactions. And we're going to react it with sodium hydroxide in different alcohol water solutions. So we're going to use methanol, ethanol, and propanol. And what we're looking at here is the overall polarity of the solvent system. As we add carbons to our alcohol, our solvent becomes less polar, right? So we're looking at the effect of the polarity of the solvent system on the reaction. Okay, now these are methanol water, or, these are alcohol waters, solvent systems. So these are all protic, which we know promotes SN1 because it tends to solvate the nucleophile and slow it down. And it tends to solvate the leaving group and therefore speed the leaving group leaving. Both of those tend to increase the rate of SN1 reactions. So here's the mechanism for that reaction, right? Our leaving group will leave a tertiary butyl carbocation behind and the bromide ion. In that basic solution, right, the hydroxide ion will act as nucleophile to complete the substitution. And so our final product will be the tertiary butyl alcohol. But what we're going to look at here is the color of phenolphthalein, right? So when we start, right, our phenolphthalein will be pink. But as we drop the concentration of hydroxide ions as they react, right, our second favorite dead French chemist, right, Le Chatelier, right, says that this reaction will shift this way to try to replace the missing hydroxide ions which will lead to more protonated, right, more of the protonated form of phenolphthalein, which is colorless. Right? So eventually, our phenolphthalein color will fade. Right? That is the indication that our reaction is proceeding, is when the phenolphthalein color fades away. Right? And so, right, we're looking at, in this case, remember, it's not about the substrate. It's about the polarity of the solvent mixture. Right? So we look for trends related to the changing polarity of the solvent mixture.